Okay, so let's say we have a car that's being lifted into the air, 2 meters into the air, and the mass of the car is 1,400 kilograms. We can assume that it's going at a constant velocity as it's being lifted up. We'll assume this is a lift, car lifting this into the air. We have the force apply going up and the force of gravity going down, and those are equal to each other in this case. So we have the force, which is 13,720 newtons, and we can calculate the work. We know the force, we know the displacement is 2 meters. The displacement is upwards, the force is upwards, so cosine is 0 degrees, and we get a work of 27,440 newton meters. So if we want to evaluate what's going on with power, power is the rate at which work is done. So what we do is we take how much work we have in joules and we divide it by the time in seconds. And this will give us watts. Watts. There we go. Capital W, watts of power. So in other words, if we do work over a small amount of time, power is big. Versus, if we're, taking a long time to do work, power is small. So in this lift example, the work, this 2 meters of work as this car is lifted into the air, if we wanted to know the power output, we would need to know something about the time. So let's assume that it took 20 seconds for this car to be lifted into the air. If that was true, we would take the work in joules or newton meters and then divide it by the time. So this is how many watts of power this lift is using to lift this into the air. Now let's say it only took 10 seconds, right? If it only took 10 seconds, our power would be 27440, same amount of work, but now it's only out of 10 meters, or 10 seconds rather. So 27440 divided by 10, so this would be twice the power, right? 2744 watts. If that was the, if it was that fast. And so that's important to consider as you're, looking at power. The time has a big impact. The unit of power is the watt, was 1 joules per second, or 1 joule per second, after James Watt, who worked on the steam engine. And you hear horsepower, we use horsepower quite a bit. 1 horsepower is equal to 746 watts. Okay, so let's bring this all together as we consider, the work changing a system and incorporating friction as well. So let's say we have a hockey puck here that's hit by this hockey player over 18 centimeters, so 0.18 meters. We have the force of the hockey stick on the puck. The puck is starting from rest, but we do have some friction. 0.08 is the coefficient of kinetic friction, and we want to find out, what's the final speed of this puck. So when we do that, we want to set up our free body diagram. We have the normal force, force of gravity, force applied, force of friction. We set up our net force. We have the positive force applied in the x plus the negative force of friction equals ma. And we have the normal force equal to the negative force of gravity. And our goal here, is to figure out again how fast is it moving. So we have our force applied in the x. We have our coefficient times the normal force. Our normal force is 2.352 newtons, which we can place in here, and we have 0.08, which is our coefficient of friction. So when we bring those together, not a whole lot of friction at all, right? 0.18816, and we add that to the frictional force here, or not frictional force, to the force applied, and so that's our net force. And so with this, we can use work net equals the change in kinetic energy, right? So work changes the energy of a system like we looked at before. We can place our values in there. In this case, the net force is in this direction, right, to the right. The displacement's to the right, so cosine is 0, and we should get a speed of 6.1 meters per second. Now, if we want to bring in power to this, we have the the time. Let's say it took 0.5 seconds to hit this hockey puck, and we want to find the power output by the player. So, we just take the work done by the player, which is 25 newtons times 0.18 meters, and divide by the time, and we get to how much work. Well, we get the power output of the player. All right, so let's next consider an airplane that's flying. Let's say the airplane is traveling 100 meters per second, and the engine produces a force, and air resistance is equal and opposite. Let's say that the force of friction is 3,720 newtons. What is the work done by the airplane over 100 meters? So we've got the force of lift, we have the force of gravity, we have force applied by the airplane, force of friction. If it's going at a constant velocity, we know that force applied and force of friction are balanced, so is lift and force of gravity. So therefore, the force applied is the same as friction, and we get 372,000 joules as the work done, by the airplane. So how much power is done in 1 second? If we take the work, which is the 372,000 joules, we divide it by the time in seconds. It turns out in this case the power output is equal the same as the work, because in 1 second it's going 100 meters. It would be different if it was going faster or slower. So another way that we can calculate power is multiplying force times time. And so we know that power equals work over time, right? What really is work? It's the force over a displacement, and then over time. So really, displacement over time is speed, and we can take that speed and know what the power output is. So if we take the same problem, we have the force and we have the speed. We can multiply those, and we'll get how much power we have. Okay, so let's go ahead and apply this to apply work to the situation of this bulldozer pushing this log to the right here, as it pushes it across the ground. Let's say the log has a mass of 1,100 kilograms. Say the coefficient of friction between the surface and the log is 0.5, and let's say it's going at a constant velocity and it's being pushed for 10 meters. We're going to find out how much work does the bulldozer do. So why don't you go ahead and pause the clip, draw your free body diagram first, then set up your net force in the x, net force in the y, and solve for how much force the bulldozer is exerting to push this log, and then you can calculate the work. So go ahead and pause the clip, and when you're ready you can continue. Okay, so normal force up, force of gravity down, force applied to the right, force of friction back. We have the net force in the x and the y. At a constant velocity, therefore acceleration is 0, so the force applied is equal to friction. And that's where we're going to need the forces in the y. We need the normal force. Normal force is 10,780 newtons. We can place that in for normal force and multiply by the coefficient, and we get a force applied of 5,390 newtons, which is also the force of friction. And so an object in motion will stay in motion at constant velocity as long as there's no net force. So in this case, the positive 5,390 is counteracted by the negative of that friction, right? We can calculate work. We take that force times the displacement, and the force applied is to the right, the displacement is to the right, so cosine of 0, we have 53,900 Newton meters of work that the bulldozer does. Let's say it took 15 seconds. How much power did it take? So why don't you go ahead and pause the clip. You can try this one. Calculate the power output of the bulldozer. Okay, So work is work over time. 3,593.3 watts is the power output of the bulldozer.